We're talking about projections, the parallel projections, technical illustrations, how to prepare these illustrations, and I will show with some examples, and this kind of examples we'll do in the laboratory classes also.
Okay, so there is a we call multi-view drawing or orthographic projections in before. Okay, so we studied like 3 view, like front view, top view, and left or right view. So those kind of views are projections of each side of the object, right? So we call this one multi-view drawing. Okay, something like this. Okay, so this is the front view. This is a front view, and that's the side view, like the left-hand side view. And that is we call multi-view drawing. So that makes it possible to accurately represent the complex forms of a design. Every complex form can be accurately shown from each side, and every side will be in own position. So that calls like multi-view drawing. Okay, so multi-view drawing includes a series of views. Okay, so many views and sections. So here you can see the half of the sectioned part, and half is outside view. Okay, so in between there is, you can see that center line. Okay, so chain line. And the second type is, okay, so that's multi-view drawing. That's a projection kind of each side. Another type of the projections is axonometric projection. So sometimes we call pictorial drawing. It looks like a picture. Okay, so from the side, like 3D. Okay, so axonometric projection make you easily understand the part, about the part, and that is necessary to communicate designs to people who do not have the technical training. Okay, so technical drawing training. Okay, so if you have no skills of technical drawing, so it's easy to understand this one. Okay, so it's easy to understand, and so, but to produce this one, to draw this one is not easy. Okay, so it's difficult. It's not accurate. Okay, so sometimes we cannot measure like from each side or like this angle. Okay, so that might be error. So the angle in reality it might be different. So you cannot measure angles from axonometric projection. And sometimes you see in axonometric projection might be different than this side projection. Okay, so multi-view projections. So that's why multi-view drawing or orthographic drawing is very accurate. Okay, so that's accurate and easy to draw. Easy to draw, but the drawback. Okay, so disadvantage of this method is bad point of this one. This method is difficult to understand. When you have technical drawing skills, if you are engineer, if you are technician, so it's good for you. But just normal common people cannot understand well. So that's why we're using axonometric projection. This one is easy to understand, easy. Okay, so easy to understand, but difficult to draw. Okay, so difficult to draw. And okay, so this is a main difference of these kind projection types. So there is a 4 types of projections, like shown with comparison. Okay, so the multi-view projection. So like a first one, multi-view projection. What's the meaning of the multi-view projection? So this is a part, the object. And so object is projected into the plane of projection. So this is taken from American book. So that's why in our case the plane of projection will be outside. Okay, so the back side, so back side of the object. Okay, so this thing will be there. Okay, all other things are similar. So we are looking to the object, And then what we see, point A, B, C, D, and corners. Okay, so A, B line, B, C, and C, D, and D, A will appear on the plane of the projection. Okay, so this is a plane of the projection. So, and line of the side will be 90 degree. Okay, so 90 degree. It will be 90 degree. Everything will be 90 degrees. So the rays. Okay, so we are seeing from each side. So that rays will be parallel and also 90 degree to the projection plane. Okay, so that's a multi-view projection. So we are looking to the front side and drawing as is, and we are looking from the top side. What we see, okay, so the looking angle is 90 degree every time. Okay, so 90 degree, and so that's why we see only sides. Okay, so that is and we will have many views. Okay, so that's why multi-view projection. Okay, so in axonometric projection we are looking with that way. Okay, so the rays are still parallel. So rays are parallel. Here you can see the rays we are looking like this, but we are seeing the object in the position of one corner and plane the ground. Okay, so that will be in between. There is a 30 degree, and another side of the corner will be 30 degree. Okay, it's not straight like this. Okay, so that is a 30 degree slope. Another side also 30 degree slope. So we are looking like that way, but still the rays, visual rays, we are looking in between. The rays are parallel. Okay, so everything are parallel here. Okay, so that is axonometric projection. And in oblique projection, so this one, in oblique projection, we are looking the side of the, okay, the similar to the multi-view projection, we are looking like straight from the floor. Okay, so it will be straight, but the side will be, okay, the rays will not be 90 degree. So here is 90 degree, but here is not 90 degree. Okay, from the side. And you see in the multi-view projection, for example, a cube or square, so the front view will be like this, and in axonometric projection the looking style, okay, will be something like this. So that is here is a 30 degree, here also 30 degree. Okay, and oblique projection, so you will see like this thing. Here the front view, and the sides will be something like this, parallel, but not perpendicular to the projection plane. So here will be 45, 60, something like that. Okay, so that's a front view, front. That's a front. Okay, so that is oblique projection. But here will be a straight, same like a level. Okay, so the floor, and here 90 degree. Okay, so the perspective projection. In the perspective projection, this one. So we are looking from the one point. Okay, so from one point we are looking to the object. So same as the multi projection, the plane of the projection will be the back side of the object. So everything appear here. Okay, so we are looking to the object from the one point, and we are the sides of the, okay, so rays of the looking is not parallel to each other. So that's why when you see this cube, that might be something like this. Okay, so the corner, you are seeing the corner, this corner, and the sides might be not parallel. Okay, something like this. You might see something like this. If you go to the to the corner to the building, so you will see something like this thing. So sides might be smaller, but your standing point, the corner looks like the longer. So something like this. You're seeing like this. If you see from the top, you will see something like this saying. Okay, but the sides, this one and that one, the first one and second edge is not equal. Okay, so different. Why? Because the rays are not parallel. So that is perspective projection. So let's see them more detail. Okay, in next slides. So here you can see the difference of perspective projection and parallel projection. So in parallel projection, so parallel, these are. So the multi projection is parallel, axonometric also parallel, and oblique are parallel. Okay, so this is a parallel projection, that is parallel projection, that is parallel projection, because of this rays are parallel. But here rays are not parallel. It starts from one point, so that is perspective projection, perspective projection. Okay. In here, perspective projection, can see the sides are not parallel, but in parallel projection, the side edges are parallel. That is actually oblique and parallel projection. That's oblique projection. That is perspective projection. And in perspective projection, you might see like this. The edges are not parallel, so you will see in some point these all edges are meeting and crossing. Okay, so the sides of this the road and the sides of this the roof points are passing through same line and then meeting in one point here. So that is perspective projection, 1 point perspective. Okay, so perspective. There's a types of perspective projection. So that is 1 point. Okay, so because it's meeting in 1 point, 1 point perspective projection. Okay, so here you might see many different types of projections. Okay, so that calls front elevation. Okay, so front view calls front elevation, and this is elevation oblique because you can see that that's kind of this parallel projection, but oblique. So here is 0 degrees, same as the floor, but here is some angle. That's why that's the oblique. That's a plane oblique. So if you see from the top side, the plane, that's a little bit the slope, so has same angle, and that's the parallel every side. Okay, so that is plane oblique, and that is isometric. So because of this, the floor, and here is 30 degree, and that's also 30 degree. So that's why that we call isometric projection, and that is 1 point perspective projection. Why? Because every side of the edges are meet in 1 point, in single point, so 1 point. So that's why 1 point perspective projection. Okay, so in 3 point perspective projection, we'll have 3 points. Okay, so the sides, like the column, if you continue columns, so you will meet somewhere one point, and the sides. Okay, so the right hand side edges, if you continue every sides, you will make some another point, second point, and the left hand side, if you continue these edges, so you will have this point 3, okay, third point. So that's why 3 point perspective projection. Okay, 3 point perspective projection. So in 1 point, so you will have only 1 point. Okay, so how about the columns? So you can see the columns are parallel. Okay, so parallel and not meet together, so that never cross with each other. So that's why we are neglecting this one. We are not taking into account this. Only one, okay, right hand side and left hand side is meeting together, making only 1 point. Okay, so that's why this is 1 point projection, perspective projection, and this is 3 point perspective projection. Okay, so how about this one in this picture? Do you have can you see this one? This one.
Yes.
Okay, so the question, okay, perspective projection, how many points are here?
I see just one.
Yes, 1 point perspective projection. So here, so every sides are meet together like this, and so only 1 point. So that's why this is 1 point perspective projection, same like this. And how about this one?
2.
Yes, 2 point perspective, similar to this one, but there is only 2 points. Like these sides are parallel. You see, parallel, so never meet, and only this side 1 point, another point is here. So we call this one left vanishing point, LVP, and right hand side vanishing point, right VP. Okay, right hand side vanishing points. So every sides are meets one of these 2 points. Okay, so left and right hand side, and we are standing on this corner, and we are looking to this 2 streets. Okay, so right hand side there's another street, and left hand side another street. So that is 2 point perspective projection. Okay, so it also has types. Okay, so later on we'll study this. Okay, how about axonometric projection? So same like the top right hand side one. So two right and left hand side has 30-degree slope. Okay, so it has also types. Okay, so it has axonometric projection has 3 types. The first one is isometric projection, just isometric projection. Isometric is like this. Okay, so when you have equal 3 3 sides, okay, so 3 directions are equal, x, y, z, okay, axis and the sides of the object or edges are same. Okay, same distance, and also the angles. Okay, so alpha, okay, a angle A and angle B and angle C are equal. Okay, so if there is, this is 360 degree, so total the circle. So 120, 120. Okay, every A is 120, C is 120, and B is 120, equal. So that is isometric. Okay, and still, okay, this one is axonometric. Axonometric is just more general description, but axonometric consists from isometric and dimetric and trimetric. So in isometric, all sides are equal and all angles are equal. In dimetric, only 2 sides are equal. Okay, so OY and OX is equal, and B, okay, A and C, in case of only angle, A and C angles are equal. Okay, but B is different, and only OX and OY is equal. So it's similar to this one, but a little bit turned. If you see in 3D, sometimes it's turned. So this side is not equal to this side. So that's why we call dimetric. Only 2 sides are 2 edges are equal and 2 angles are equal. Okay, so dimetric. D means 2. And in trimetric, none of the sides are equal. Okay, so all edges are not equal, unequal, and all angles also unequal. Okay, so this is trimetric. So these, okay, 3 of them we are using in when we work with 3D information in the software, in the computer. But in technical drawing, in hand drawing, or just instrument based drawing, we are drawing isometric projection, because to draw this one is very difficult by your hand. You know, in the computer it's easy, but by your hand to generate this one is difficult. So you might have many errors. So that's why isometric projection, we study an isometric projection. When we call axonometric projection, sometimes we do isometric projections. Once you do isometric projection, and you can able to generate in the computer these other two. Okay? So okay, let's see next one. Okay, so 120, 120, 120. So if we divide 360 degree to the three angle, and also the two sides should be 30, 30. Okay, and all other sides also. So the rhombus, inside the rhombus, so in here also it should be 360. So if you divide to 4, you will have like okay, so this one is 120, so another side also 120, so 240, 240. So 360 minus 240 is 120, 120. So 120, if you divide 120 to 2, so you will have 60. Okay, so that's why here is 60, and right hand side also 60, 60, 60. So and same to this side also. Okay, 360. So here is 120, and here also 120. So other sides will be 60 and 60. So right hand side also similar. Okay, so how to draw this one? So you have instruments. You have instruments. You do a line like this, or if you have graph page on your sheet. Okay, so graph marks. So to that line, so make any one dot, and then to the one side you can put your tools and make a 30-degree angle. Okay, so if you have no tools, no any compass, no any protractor, so how to measure this distance? Just you measure. You can use the cells. Okay, so like if you have graph paper, so make once just measure one cell, second one, third one, fourth one, and fifth one. Okay, so 5 cells to the right hand side and 3 cells to the upper side. 1, 2, 3. So then connect these two, so you will get 30-degree. Okay, so if you have no graph paper, so what you do, just measure 2.5 centimeter, 2.5 centimeter, that is 5 cells. Okay, 2.5 centimeter to the right hand side, and the upper side 3 cells means 1.5 centimeter, or same like that is 2.5, right? 0.5. You can do, if you have a bigger page or bigger drawing, so you can do like 5 centimeter and 3 centimeter here. Okay, so you can do 3, and here is same like 5.
The main is proportion 5 to
Yes,
3.
yes, 5 to 3. Just remember 5 to 3. To this side also, to the left hand side also similar, 5 to 3, 5 to 3. And from this point also you can make a just thin line and make a 5 to 3 in order to draw kind of a rhombus. And the rhombus means the base of the cube, or base of some prism, which is the kind of square shape. Okay, so square shape looks in isometric projection kind of a rhombus. Okay, so the square shape is in isometric projection looks like rhombus. And also the circle is also looks like an oval. Okay, isometric oval, we call isometric oval. Okay, so that will be, the oval will be inside of this rhombus. So to draw the oval, isometric oval, you need to draw first this kind of rhombus, and then inside of this you can draw your oval. Okay, so that's
there was one rule to draw non-isometric lines like this, the line. Okay, so non-isometric line, how to draw this one. So there was one technique. So we have seen in example how to generate this kind of thing. And also the angles, also non-isometric, okay, the angles in isometric projection should not be transferred from the orthographic projection. So there was an example, another example. And there was an example of how to draw irregular part, like non-isometric again. So the corners of this pyramid is not isometric line, so that's why there was a technique to make a box and then to find the points and with measure from the corner of the box, the prism, and to find the points, and then we can connect that points to generate the shape in isometric projection. And there was an example of to generate a curvy lines, curve thing given in orthographic projection, have to generate an isometric projection. So there was a technique by making cross sections of it, and then using that cross section points to generate the curve in isometric projection. So there was another example. Okay, so isometric to make isometric drawings, sometimes we have to represent the circle, a circle, and so that circle is based on the side of the shape. It might be differently positioned. So in this example, we have seen the different three types of positions. Okay, so left hand side, right hand side, or top side of the plane. The ellipses differently should be represented. So here is some example is shown, and here the arc as the part of the circle, it should be drawn as an ellipse in isometric drawing. So we have started how to make isometric sectioning, the rules, and isometric dimensioning. So this was the last slide from the last lesson. So the isometric dimensioning is three types. Okay, so aligned, unidirectional, and some example of some incorrect one. Okay, so aligned and unidirectional. So we are using in most cases aligned one. Okay, so unidirectional is also can be used, but we prefer to use aligned one, and we prefer to use the second example. Use this kind of dimensioning style. Dimension value should be on top of the dimension line. Okay, so dimension line should be under the value. So in first example, there is some disconnection, so we prefer to make without any disconnection. Just draw a line, dimension line, and on top of this write the value. In dimetric drawings, that is also axonometric projection type, but in dimetric, two sides, okay, two edges and two angles are equal. So here you can see two angles, okay, so 126 and 126, okay, are equal. and also the 1 inch and 1 inch left hand side and right hand side are equal. And it might be differently done like in B, so still 2 angles and 2 sides are equal. So this is example of the dimetric drawings, like 2 sides, and you can make differently check make like 45 degree here, but in here differently shown like 7 degree and 30 minutes. So here the oblique projection is shown with different, okay, the compared with perspective projection. So on the left hand side here you can see the train road, train pass in A perspective projection, and in B oblique projection. The oblique projection is usually is done with 45 degree angle, but here this side is the street, okay, straight line, and then here it will be 45 degree. So here you can see the difference of isometric and oblique projection. In isometric projection, as I told you, the circles drawn as an ellipse, and in oblique projection you draw as a circle as a circle. And in isometric projection, as so we have studied already, so it will be something like left hand side of the cube, okay? Left hand side of the cube like this. If the shape, the circle is somewhere on the right hand side, this right side of the drawn shape, so it would be a little bit inclined to the right hand side like this. Okay. If on the top, so it will be something like this shape. Okay. Okay, so here you can see the different types of the projections. The Cavalier projection or cabinet projection. Cabinet projection is used in to draw or to represent furniture industry. The Cavalier projection is used in ancient books. So the proportion of the shape is like 1, and the side of also 1 here in Cavalier projection. In cabinet projection is mostly used the side, the proportion is 50% of the front projection, front length, 0.75, so 75% of front length. So there are recommendations on positioning. So here you can see the good ways of projection, positioning, okay, and bad one, not good one, not recommended one. In good, correct positioning, we are able to see the length of the shape. Okay, so we can understand how big is this side of the part. So if you position in this way, the position the object in this way, so you cannot measure the distance. Just you cannot roughly understand how big is it. Okay? So and for this example also same, like if you position like this, is not looking well, it's not looking similar to reality. So but in this example it looks like in real part, and same as this one. Okay, so it's positioned not well. So but if you make a position from the side of this, okay, so as a front view, So you can measure, or you can just roughly understand, roughly imagine the shape, sizes. So another term is technical illustration. So engineers should understand, should produce well the all types of technical illustration. So technical illustration is the use of illustration to visually communicate information of technical nature. Okay. So by using technical illustration, you are able to, the engineers able to show their, idea in their, what they want to talk, instead of using literal words. So they're using visually communication techniques. Okay, so that calls technical illustration. Technical illustration can be components of technical drawings or diagrams. It might be some part of the technical drawing, or some part of a diagram. Okay, so technical illustration generally have to describe and explain the subjects to a non-technical audience. In most cases, we are using a technical illustration for non-technical audience, or for the audience who is not having technical skills. Okay, so technician or engineering or technical drawing skills. So therefore the visual image should be accurate in terms of dimensions and proportions, and should provide an overall impression of what an object is or does. Okay, so it should easily to understand, it should be easily to understand. So for example, this is a car, so it's by just one time seeing of this, it should be able to understand. Okay, so so this is car or not, or another object. Okay, to enhance the viewer's interest and understanding. So there are two examples of technical illustration. The first one is the illustration of the cable inside a computer case. Okay, so here, this one. So it might be shown how to assemble this, or how to maintain, do some kind of maintenance job in order to work computer correctly. So something like that. To explain this one, we need kind of technical illustration. So another illustration in the right hand side, so it's a car's technical illustrations. So some part of, or some system of the car is shown inside. It might be included in kind of maintenance book, or handbook of the car. So mostly engineers are providing that kind of manuals, technical manuals for clients, and they have to prepare that illustration when they are inventing, or they're manufacturing any goods or products. So they have to provide this kind of illustration inside the books. So communication types. Okay, so there are some spatial types of the communications. So we said visually, so technical illustration is we use in visually communication. Okay, so there is a types of communication between between the people, so between the engineers and non-engineer people, or engineers and engineers. Okay, so three types. So first one is communication with the general public. Okay, so what includes? Okay, so that's illustrated instructions. Okay, so illustrations with picture, with drawings. Okay, and manuals and simple term. They're using in this documentation, in this kind of manuals or instructions, they're using simple terminology. So they're using common words in order to explain the part, or how to maintain correctly. The second type is specialized engineering or scientific communication. Okay, so
the communication between engineers, okay, so specialized engineers or some kind of scientific community. Okay, so they're using a complex terminology. They might use specialized symbols, okay, something like this. So electronic kind of circuit design. They're using kind of special terminology, special symbols. And third one is communication between highly skilled experts. Okay, so as also it might be engineer, but it might be very narrow type of engineers, and in between that only that certain type of that engineers might use their own words, own terminology. So illustrations in user operator documentation might be only some field of engineering they're using that kind of terminology. Okay, so for example, in this examination, so this is Apollo command module main control panel. So we don't know what kind of things are done here. Only Apollo rocket or Apollo spaceship users or engineers might understand that thing. It's not widely used, so that's why it might be very specific terminology is included in there. Okay, but this one is widely used in engineering, widely used in electronics, so that's why many all electronic engineers might understand this kind of circuits. But this one is only who is working in specific products, in specific systems. They might understand and might use that communication type. Okay. So another type of communication is, okay, so types of drawings. So there are types of the drawings. Drawings also communication thing. Okay, so main types of drawings in technical communication are conventional line drawings. So that is a kind of this one. So we call pictorial drawing also. Okay, so that's just it's kind of a isometric view or it kind of axonometric view, but only the lines. Okay, so it uses the line without having kind of the color inside, without having kind of highlight the shadow highlighted, or and without any texture included inside. Okay, so just only the line, black line. And the second type is exploded view drawing. So this one. So you see that the assembly is exploded, kind of dismounted. So every part is dismounted, and you are able to see the item part names or the tags. Okay, so numbers of the part. Okay, so position like first, two, second, 1, 2, 3, 4, 5, and then on the side it will be the part name. Okay, so what's a 1, what's a 2, what's a 3. Okay, so that we call that exploded view drawing. So in this case, you are able to see, understand the part and which part should connect with which one. Okay, and how to assemble. And the third one is we call cutaway drawings. That is something like this. So sectioned view. Okay, so it's shown a sectioned view drawings. Okay, so the drawing which have half section or full section, so it's shown inside components in order to see what kind of part is included inside, or how it works, some kind of mechanisms, how they work. Okay, so those things we call cutaway drawings or section view drawing. And fourth one, in some cases we don't need to have such very complex thing to show something to people. Okay, so we might use kind of clip art
image and just simple information informations on the door or on the wall. Okay, so that means like we by using this kind of image we are having kind of notice or caution. Okay, so to the normal people. Okay, so let me show the example of the type of the drawings in technical way. So this is an example of illustration of the house and with communications inside. Okay. It's a rendered illustration. So cutaway drawings of an aircraft engine. So inside you can see that. So all components are included inside. So rendered again is rendered assembly. So the car. Okay, so this is just designed car. It's not manufactured. Just only 3D assembly shape with rendered view. Okay, so with shadow, with texture is shown. So this is exploded view of an assembly. So you can see the parts in different location. So more clear visualization is possible in this way. So this is kind of the rendered image. Okay, so illustration. So the human or worker is also is not real, and also these machines are not real, as everything are here made it in 3D and it's not real. So before doing or before making this work in the computer, it might done and to see, to plan this kind of equipments. Okay. Here we can see then an assembly is done in 3D software, and also this can be shown as a technical illustration. So technical illustration might be an animated and non-animated one. So non-animated one, to create a non-animated technical illustration, you can use a CAD software. So there is a special tools for that. Like we can change the transparency of the shape, the part, save this one EPS format, and open in Illustrator, Adobe Illustrator. Open that file so we can see the so we unghost this upper elements, and we can change the transparency here to the 30% visible, and save it again on top of the EPS file. So jump to the Illustrator and open it, EPS, and so you can see, you are able to see the file, the shape. So here is another example. Is shown a user manual a sea scooter. So the sea scooter is used underwater, so under the sea, to to use them is under the sea. Okay, so in the user manual, it might be added the information about the part list, information about all parts included inside the product, and the part names, so how many quantities of included, and is shown with balloon tags. Okay, so how to assemble, so assembly guides also might be included, and those all things can be automated instead of drawing yourself every time. So it might be automated just once you model and assemble in 3D software, so you can be able to just insert already done parts inside this manual, and that manual can be automatically rapidly just changing. If you change inside your 3D model, so the manual also will change automatically. And also you can able to make interactive 3D documentation, 3D interactive information for engineers or who is using this for the users also. Okay, so in the interactive manual, so the users might not need it to have a CAD software, just simple software with open, free, open source software. It might be opened. This kind of ready done manuals. So here you can see the example of that manual. So if you go there, if you go to the name of the part, so that will be highlighted with color, and so name and quantity, and so how to dismount and disassemble of this part is shown here. Just you can go and just click on the button. So here you can see the battery removal process. Easily you can see how it should be removed. With descriptions here you can see. So you can prepare this kind of thing. So and that one is kind of new generation of technical illustration. So you can put some buttons like automatic buttons. So you can show the sequence of assembly, and you can go to the home, the beginning position of the so you can add some text in order to make easy understanding.